Hei, og god morgen alle sammen. Velkommen til God forskermorgen, som vi nå setter i gang andre runde av. God forskermorgen er et samarbeid mellom HydroCen og Multiconsult, med det formålet å presentere rykende fersk, ny og relevant forskning innenfor både fornybar energi og vannkraft. Mitt navn er Fredrik Valstad, jeg jobber til daglig som seksjonsleder på vannkraft i Multiconsult. Vi prøver å holde dette webinaret månedlig fremover, og det vil holdes på en blanding av norsk og engelsk, avhengig av hvem som presenterer den aktuelle dagen. Og i dag det Bibek som skal presentere, og jeg går derfor over på engelsk siden han skal holde sin presentasjon på engelsk i dag. Good morning, everyone, and welcome to this webinar series, directly translated to Good Morning Scientists. This is a collaboration between HydroCen and Multiconsult, and the goal of this webinar series is to provide new and relevant research within the fields of renewable energy and hydropower. Today we are happy to have Bibek Neupane with us, and he will today present presentation with the topic long-term impact on unlined hydropower tunnels due to frequent start-stop sequences. So the presentation will last for about 30 minutes, and then we have added time for Q&A afterwards. So you can all leave your questions in the chat, and then we will take them up at the end. We are also recording this session, and we will also upload this presentation to YouTube afterwards. So with that, I'll leave it to you, Bibek.
Thank you, Fredrik, for the introduction. As Fredrik said, that is the title of my presentation today and also the title of my PhD thesis. Professor Krishnapanthy has been the main supervisor of my study, and Associate Professor Kasper Vareide is the co-supervisor of this work. Now I'd like to begin with the content. I'd like to begin with maybe a bit of a larger picture so as to put things in perspective. Here I present the gross electricity generation from different renewable sources in the EU member states for some years in the past. You can see in the graph that the production of hydropower has been constant almost over the years. But whatever increase in the production of renewable energy there is recently has been because of solar and wind. So the data is until 2016, that is the recent data I could find, but I'm sure that this has gone much, much higher now, and the share of wind and solar power now is much, much higher as compared to hydropower, or maybe getting higher or relatively comparable at least. And if you look at the other graph on the right side here, it shows a prediction of global power production at the year 2050. And it is seen that more than half of the production is from solar and wind, and hydropower is a very small part of the energy mix in the future. That's of course very nice to have more renewable energy, but the challenge with having more solar and wind power in the grid is that these sources are so-called intermittent sources or unregulated sources, meaning they can produce only when the sun or wind is available in the system. When it is not, then it has to be fulfilled by any other source, so to say as a battery, for example. That means that we need certain flexibility in the system for whatever inflexibility in the system created by intermittent sources. So we need that flexibility to create a balance between production and consumption, of course. And there are various sources that are competing to provide that flexibility or that balance, for example. And that flexibility actually is needed in different time scales. For example, short time scales within an hour, within a day, within a week, or within a month or years, for example, like a baseload plant. The data shows that, or previous studies have shown that, the changes in demand for short-term flexibility is increasing, and it will decrease the demand for base load in the future. And as you can see here in the graph, there are different sources that are competing to provide that flexibility. gas, coal, hydro, and something else. And if you look at the tick boxes for each and every source there, some sources are able to provide short-term flexibility, and some sources are able to provide only long-term flexibility like that. For example, a nuclear power plant will be able to produce or give long-term flexibility, and they're not able to give us short-term flexibility. But if we look at hydro here, that is our main focus for today, it is able to provide us whatever kind of flexibility we need. So in other words, so to say, hydropower can act as a battery for providing that flexibility that we need in the system when we have more intermittent energy sources in the energy grid. That brings us to the main topic of how the hydropower plant is being operated today and how that will be operated in the future. So since there is going to be, or at least there is now some difference in the production and consumption, that will also create differences in power prices during the day and during the seasons, of course. And to take benefit from that multiple power prices, the load in the power plant has to be changed frequently, meaning the power plant has to be operated at different capacities throughout the day or throughout the week or at different time scales. Such an operation is called hydro peaking in general terms. If you look at the figure here, this is a schematic illustration of that. For example, the power plant has been shut off for some time here. Then it goes on, operates for some time, gives us some power. Then it turns off again, stays off for some time, opens up again at a smaller capacity than the previous one. So it can be turned off and on various times, multiple times, and can be run at different capacities during that period. As I said earlier, this is called hydro peaking, and that actually has been in effect in Norway since 1991, when the power market was deregulated so as to create a more competitive market in Norway. Of course, as I mentioned earlier in the previous graph, there was not a lot of contribution of wind and sun or intermittent sources in the 1990s, of course, but still the practice of hydro peaking started back then to create room for a more competitive market. And now in the present context, and maybe also in the future, when more wind and sun is coming into the energy mix, this kind of operation will still continue and may even go further in a higher degree. So to say, most likely more rapid load changes and more dynamic operation of the hydropower plants. This next slide is actually a part of the result from my own work, where I have analyzed about 20 years of operation data from 10 power plants having 21 generating units of different sizes. This particular graph shows the number of starts and stops that occurred in power plants during that time frame. As you can see here, the number of start stops on an average is somewhere between 200 to 400. The power plants that we've taken here have different modes of operation. For example, Roskrepp and Driva have some operational restrictions to hydro peaking because of some environmental reasons. Duge is a pump storage plant, and all the other plants have no restrictions against any kind of operation. So we can see here that the power plant with, for example, Roskrepp having some restrictions against hydro peaking has a very small number of, or relatively smaller number of start stops. And the standard deviation and the minimum and maximum values are also not that far off from the average, meaning the operation of that particular power plant is not so dynamic. It's more or less steady. As compared to, for example, Onasira here, we have more than 400 starts and stops per year on an average, and the standard deviation and minimum and maximum value in this data set is actually quite high. So this shows that the operation is very random, may depend upon many factors such as hydrology and the energy market and the condition of the power plant, so on and so forth. But the point is that the operation is very dynamic and depends upon different power plants on the operation mode of individual power plants. The next graph is the continuation of a similar study in the same power plants, but this shows the magnitude of the load changes in these power plants. For example, these different colors of the bars that are shown, it shows a different magnitude of load change. For example, if we say, if we see a generating unit of 100 megawatt, it will be able to produce 100 megawatt hours in an hour. And this category here represents the number of load changes or the percentage of total load changes within that range. For example, smaller than 25 megawatt hours in this category, and so on with the other categories as well. And the blue line that you see here is the sum of all the load changes that occurred in these individual power plants. As we can see here, there are more than 1,000 load changes occurring in every power plant in a year, except for Duge, of course, because this is a pump storage, as I already mentioned. That's why probably the operation is governed by the peaking of, the pumping operation. But other than that, all the other power plants have more than 1,000 load changes every year of varying degrees, as you can see. So these two graphs shows how the power plants are being operated in Norway until now, as a result of maybe both the energy market and maybe also partly because of the inclusion of intermittent energy over the years. That leads us to the question of what happens in the tunnels when we do these individual load changes, for example. If you look at the top figure here, I presented a basic layout of a power plant called Roskrepp in the southern Norway that belongs to the Sirakvina River Valley System, Sirakvina Power Company. An upper reservoir and a brook intake, surge tank, headrace tunnel that is unlined, a small line section, powerhouse, and a lower reservoir. And this is a measurement location, which I will describe later on, where we have done some measurements for this study. And this particular graph further down shows the measurement of water pressure that is measured at that particular location for a week. As we can see that there are at least around 2 major transients per day on an average within this time frame. So that is, let's say, the number of load changes that have occurred within this time frame, and that is translated to these pressure transients in the tunnel system that was recorded here. And if you look at this particular graph on the right, this is just an enlargement of one of the pressure transients. For example, here we have the static condition before the transient or the load change began. Here, the shutdown of the turbine valves began, and that induced a transient like that. That is the mass oscillation peak, and that is the water hammer peak. And the transient goes on until it is dissipated totally by friction. That is a typical example of a pressure transient that occurs with every load change or every start or stop. Not start, but stop, of course. Stop will have a different kind of pressure transient, of course, but this is a pressure transient resultant from a stopping event. As you can see, the water hammer will travel between the powerhouse and the surge tank, and the mass oscillation will travel between the surge tank and the reservoirs. So they have different areas of application, so as to say. So the whole point here is that the energy mix in the global power market is changing over the years, causing more frequent start and stop sequences, and causing more pressure transients in the system. And that means that the power plants are most likely being operated now as peaking plants rather than baseload plants, which more or less occur or operate at a constant load. So the operational regime is changing in simple words. Now we look at the design criteria that we use for designing unlined pressure tunnels. Um, um, the design criteria until now is basically focused on making the tunnel safe against hydraulic jacking or uplifting in different operating conditions. For example, at static condition, the factor of safety is 1.3. In surge conditions, the factor of safety is 1.1, meaning the factor of safety against the water pressure during mass oscillations. And the design criteria says that we don't need any factor of safety for water hammer because they are very fast. As you can see, they occur within a very small time frame. And that's why the time period of application of this hydraulic stress because of water hammer is very small. That's why we don't need any factor of safety for design. That is the gist of the design criteria that we use. So the design criteria basically covers the factor of safety against hydraulic jacking, but it doesn't say anything about the safety against the effect of frequent load changes that are occurring, at least now. But in the past, there have been at least some minor discussions about what will happen if there will be frequent pressure pulsations in the future. I'd like to read this line that says, if the operational requirements lead to frequent pressure pulsations, special force efforts may be needed to ensure that blocky unlined sections remain stable, operational over the lifetime of the project. So maybe there's some hint about this will happen in the future and that might create some problems. So it says that if there are some frequent pressure pulsations, that might create some problems in the future. But based on my study that I've done over these years, I have not come across any other literature that specifically studies this particular issue in detail. And that is what we have done in this study. And I will, from the next slide, try to explain what we have done. So on the left figure here, you see an example of what a tunnel looks like and the water pressure that is acting on a tunnel with some flow occurring through the joints. When the water pressure in the tunnel is in static condition, it will induce some flow through the joints and some pressure situation in the joints, which will reduce the effective stresses in the joints, of course. That will cause some minor flow out of the tunnel. And the design criteria, as per the design criteria, if that does not cause any hydraulic jacking and the leakage is within acceptable limits, then we accept the design and we go further with the operation of the power plant. But when the pressure changes here during a pressure transient, something changes around the rock mass here. For example, the pore pressure in these joints that are close to the tunnel itself changes, and that will create some additional forces on the joints like these, which we think might be the source of some instabilities like these that we've seen when we have visited these some of the tunnels during this study. For example, we can see some blockfalls here and here as well. We will try to link, or we will try to explain what happens when we induce a pressure transient here based on some measurements that we've done in Roskrepp again. That is the content of my next slide. So this is a plan view and a detailed view of an instrumentation program that we've installed in Roskrepp in June 2018. This instrument is still recording the pressures from the tunnel and the rock mass. The basic gist here is to record the rock mass pore pressure when the power plant is being operated. For that, if you look at this figure, we have an unlined section of the tunnel here until this point, and here begins the steel line section of that tunnel. That's the direction of the flow. That's an access tunnel coming into the headrest tunnel with a concrete plug and a steel gate. What we've done here is we've drilled 5 boreholes in different directions, which I'll come to later on, and installed a combination of packer and steel pipes to record the pore pressure in the rock. We brought out these pipes out of the headrest tunnel to a dry area out of the steel gate here, and installed pressure sensors and a data logger to record the data. But before that, I'd like to explain a little bit about the figure on the right. These are the orientation of each borehole here that intersects a particular joint set um, as perpendicular as possible. And if you see the red section here, that section is the section behind the packer and is grouted. And this is the blue section is collecting the water from the rock mass that has traveled from the joint, so to say. So this pressure measured by the sensor will record the rock mass pore pressure for all the cases. Some more detailed figures of the same arrangement. That's how the tunnel looks like. These are the 5 boreholes that we've drilled and installed the packer. And that's how it looks from the outside. The packer is inside, of course, and a pipe is coming out. And that pipe is going out to the dry area, as I mentioned. And we've also simultaneously measured the water pressure at the tunnel at the same location. So a cross section of what is happening inside the borehole here. The section of the borehole that collects water, the packer, and the grouted section. So what the packer and grouted section does here is creates a barrier between the tunnel water pressure and the rock mass pore pressure, so that there is no direct hydraulic connection between the tunnel and the rock mass here. So that water pressure goes out through the pipe and towards the dry area where it is connected to a pressure sensor like that. And that pressure sensor measures the pressure values from the rock mass and is being recorded by the data logger here that you can see, the pressure sensor and the data logger. And this data logger measures pressure readings at a rate of 10 data every second. And this has been measuring data for more than 3 years now. And the further results from this instrumentation are the main focus of the results that I'm explaining today and the findings that I'm explaining today. So this is what the result looks like. I've chosen to present the data from the pressure readings from the tunnel pressure, of course, and the readings from 3 different boreholes. As you can see, the blue line is the tunnel pressure during the pressure transient here. That shows the mass oscillation peak and the water hammer peak. And also the pore pressure readings, for example, from somewhere down in the rock here for 3 boreholes. Borehole number 1 is what I like to call a responsive borehole, for example, because it responds very well to the pressure transient in the tunnel. It actually follows quite well with the tunnel pressure, right? Borehole number 2 is what I call a non-responsive borehole because it doesn't respond to the pressure transient at all. Borehole number 4 is also a responsive borehole, but it has a certain time lag, so to say, because the pressure peak is the tunnel pressure peak is here and the rock mass pressure peak is here. So there's a certain time lag between these 2 pressure peaks, and also the pressure magnitude is reduced, probably because of friction. So the reason these boreholes are acting as responsive or non-responsive is, of course, the properties of the joint. For example, borehole 2 and 4 is what we've recorded from our joint mapping before installing these equipment is that they are partly open and open joints with some conductivity in these joints. And borehole 2, these are tight joints and they do not conduct any water, so that's why they do not respond to the pressure transients. So now the main focus is for the responsive joints, number 1 and number 4, especially for example, let's say number 4. Because of this time lag that we see here, at some points along the pressure transient, it happens that the tunnel pressure is actually lower than the rock mass pore pressure, meaning that the resultant pressure is higher in the rock. That actually tends to push the block a little bit out during these events that are highlighted here, for example, with the gray shade. This and this, and similarly for borehole 1 during a water hammer event like that, but that occurs for a very small time. We have called this area or this additional force as we've termed this thing as hydraulic impact, and this is an integration of the pressure versus time, a multiplication of these two parameters that gives us a relative measure of that additional stress acting at that particular point in the rock mass during each pressure transient. So we see that for responsive joints during a pressure transient, when the pore pressure in the rock mass is higher, there will be some additional forces that will act on the rock mass that tends to push the rock a little bit out into the tunnel. So that is an additional stress that we induce when we experience a transient because of a load change, and that we do every time when we change a load or a shutdown or an opening. So we induce some load, some additional stress every time we change something in the power plant. That is the main result here. I'd like to draw your attention to a term that I've used that's called a shutdown duration here. And that duration is the time period or the time between when the shutdown was started and when the mass oscillation peak reaches its maximum value like that. I will explain what happens when we have different shutdown durations in the next graph or the next slide. Here in this slide, I present two pressure transients of similar magnitude, but having different shutdown durations, so to say. For example, this is the full transient event, or not the full, but a larger time period of these two transient events lasting for more than 1,000 seconds. And you can see that they have different nature of graphs, different shutdown durations, which I will explain using this graph here. So the graph on the right side is just an expansion of this particular section of the graph here. So if you look at this particular graph here, the duration for the final shutdown, meaning the location of peak water hammer pressures are almost the same. The peak for the red and the blue water hammer peaks are almost the same. But we see that the nature of the pressure pulse are different here. As you can see in the blue line, it is a bit more steeper and it acts a bit more rapidly. As compared to the red line, it is a bit more, let's say, gradual, with some series of events that are occurring that is more gradual, right? So when we do this, what happens is that, for example, when we have a gradual closure of the turbine valves, the guide vanes, we see that the rock mass pressure is actually following very easily, very close to the tunnel pressure, as compared to when we do it very rapidly. That means the time lag is much, much higher when we close it very rapidly. And also the pressure rise is actually something that creates a larger hydraulic impact when we close the turbine valves very rapidly, or in other words, when the shutdown duration is short. So for the blue line or the transient 2, second transient, the shutdown duration is very short, 63 seconds. For transient 1, the shutdown duration is long, almost 150 seconds. So the point is, when we close the turbine valves very fast, we create a larger hydraulic stress or larger hydraulic impact in the rock mass. That is one of the major findings that we have. And this is a comparison of two transient events. The next finding that we have found out is that we have seen that the shutdown duration for various transients, it's very different. As you can see from the graph here, there are different clusters of shutdown duration. For example, there's one cluster with shutdown durations that is less than 80 seconds. Another one may be something between 120 and 140, a third cluster around 140, and another cluster that is higher than that, right? So from the previous discussion, this cluster would probably be the most safest in terms of inducing lesser hydraulic stresses, and this would create a larger hydraulic stress in the rock mass. But here we can also see that these shutdown durations are different even for a similar magnitude of the load change. For example, here on the x-axis you can see the head loss before transient. That means for a same value of head loss before transient, this means that they will have equal amount of flow. For example, two shutdown events with equal amount of flow before the shutdown are being actually shut down at two different time periods. Similar magnitude load changes are being done differently. For example, one let's say is being done at 50 seconds and the other one is being done at, let's say, more than 160 seconds, similar to this, for example, right? So and we know that there is not we don't have a standard procedure for doing these shutdowns, and these are based on solely on on an individual power plant operator. For example, if someone wants to do a load change from 50 megawatt to 0 megawatt, it can be done in, like, let's say 160 seconds or 50 seconds, as you can see in the graph. But we've seen from the results that that causes some difference in the effect that we cause in the rock mass. So this is significant, because if we can do a shutdown in a proper manner with a slow shutdown duration, we can actually avoid a lot of hydraulic stress as compared to when we do it very fast. So that's why this is significant. If we compare the results of all these shutdowns, for example, when we do a shutdown duration slower, we create smaller hydraulic impact as compared to when we do shutdowns with smaller shutdown duration. So here, for smaller shutdown durations, ranging from 50 to 75 seconds, the hydraulic impact that we have created in the rock mass is of a larger range as compared to the shutdowns with larger shutdown durations. We have smaller hydraulic impact. And we see that the shutdown duration, when it's doubled, the hydraulic impact was as high as 10 times in the rock mass. So the main gist of these findings is that if we do slower shutdowns and openings, we will reduce the additional loading of the rock mass and may most likely slow down the fatigue of the rock mass that will occur because of these power plants over many load changes that we do over, let's say, 30 or 50 years of operation of the power plant. This is what we have recorded from Roskrepp, and a summary of results from I think about 2 years of operation of 2 years of data from Roskrepp. We've done some numerical simulations using the same data. We validated the numerical model using the measured data, and try to do something with the models to see what happens when we change some input parameters in this model. So here you see a block of rock mass with a joint indicated by two different colors and a tunnel crossing that joint, cross section of that. And we have measured, for example, we have simulated the joint pore pressure that we measured in the rock mass when we change something in the tunnel, and the normal displacement of the joint and flow through the joints, the rock joint, when we, let's say, for example, do the tunnel filling or induce a transient in the tunnel. We've done a numerical simulation for different input parameters. For example, what happens when we change the static head of the tunnel? What happens when we change the time period of oscillation, for example? What happens during a water hammer, and what happens during a mass oscillation? And also to see the effect of various rock mass properties. I will only explain a part of this result. The simulation step is something that we usually do in real practice. We excavate the tunnel and we fill the tunnel. And we've also done the same in the model to simulate the filling, so that we can actually induce some joint deformation before we induce the transient itself as a result of tunnel filling. And then finally, we induce a tunnel pulse to simulate a pressure transient like that. So this is a result of a pressure transient that we've induced in the model. For example, here, again, the blue line, the topmost line, indicates the tunnel pressure that we've induced here. And all the other lines show the rock mass pore pressure at different locations along the tunnel, along the tunnel wall as we go deeper into the wall, for example, 1 meter, 1.5, 2.33, and so on. So all these dots indicate different points along that tunnel wall and this one. So the results here, we can see that when we are closer to the tunnel wall, the pressure magnitude is actually higher. And there's some certain time lag, of course. And when we go further into the rock mass, the pressure magnitude decreases, of course, but the time lag goes on increasing, right? So that again translates to some hydraulic impact at each of these locations, because hydraulic impact, as I already explained, is the area between each of these curves. For example, if we see this red curve and the blue curve, the hydraulic impact is that area, and that changes for every other point along that graph. So that is something that we see. And for this particular result here, we've used a time period of 3.5 seconds. For example, the transient starts here and ends here. So it has a time period of around 3.5 seconds, meaning we've simulated a water hammer pulse here. I've simulated pressure pulses with different time periods. For example, this one is the same as I showed, 3.5 seconds, and I've used different time periods, of course, 60, 120, 200, and other something else as well. And the results show the hydraulic impact at one particular location. I think this is at 2.3 meters in the joint. Along the length of the joint, that's along the length of the joint and the hydraulic impact. So we see here that the hydraulic impact, or the additional hydraulic stress that we've created with a water hammer, for example, the blue line, is much smaller as compared to the hydraulic impact or hydraulic stress that we've created using mass oscillation. For example, let's say 200 seconds. It is very high as compared to this one, which is reasonable as well, because the time of application of this hydraulic stress is much larger, because the mass oscillation will remain in the rock mass, or the effect of water hammer will remain in the rock mass for a larger time. Or in simple words, the pore pressure will be trapped in the rock mass for a longer time. But if you look at the graph on the right side, we see that the deformation is not that different. For example, even though the deformation values along the joint is almost similar for the mass oscillations, and also probably for the water hammer as well, the hydraulic impact is quite large actually. So the hydraulic impact is the result of, at least for mass oscillation, is a result of that pore pressure being trapped into the rock mass for a longer period of time. So larger the time period, more will be the hydraulic impact in the rock mass, is the summary of this result. So larger time period will cause large hydraulic stresses, and that will also be felt deeper into the rock mass. For example, here, when we increase the time period, it is gone deeper and deeper into the rock mass like that, right? So that is the summary of the result when we change the time period of oscillation of the pressure pulses. So as a result of all these measurement results and simulations, and based on the observations that we've done of some tunnels during this period, we have developed a sort of a model to explain how the fatigue develops in a rock mass, which could potentially lead to a blockfall, for example. Here I've shown a situation in a tunnel where there's a set of joints, for example, 2 sets of joints, and I've chosen some locations around that intact rock piece or around that joint to show the pressure situation when a pressure transient occurs here and what happens to the resultant pressure or the direction of the block along the pressure transient. As we can see here, this particular situation of joints is not giving us a situation that will readily create a block fall, because we have an intact rock bridge, so to say, that is stopping this piece of rock from falling down into the tunnel. So this is still stable and might be left unsupported, for example, right? So what happens when we induce a pressure transient like what we just saw in the previous slides, for example? Again, tunnel pressure given by blue line and all the other tunnel pressures, rock mass pore pressures at different locations like that. We see that closer to the tunnel wall, the pore pressure in the rock mass will again follow closely, as we've seen previously. As we go further deep, the time lag will increase, but the pressure magnitude will decrease like that. At some location far off, the pressure transient will probably not travel that deep, so it will most likely be behaving like an unresponsive joint, because that is probably a bit far off as well. Again, the hydraulic impact at one particular location, hydraulic impact at B, is shown by the shaded area. Below, I have shown the direction of the resultant pressure at different time stamps during the pressure pulse. For example, at time equal to 0 here, this is the situation because all the other pressures in the rock mass in the joint is smaller than the tunnel pressure. So the resultant pressure direction is moving up, so to say, tending to push this block up like that into the rock wall. When we move further along the time period here, that will increase because the difference is increasing, the resultant difference is increasing like that. At a different time scale, actually, what happens is the tunnel pore pressure is actually less. For example, at point B, smaller than tunnel pore pressure in the tunnel. That means there will be a negative direction of resultant pressure, meaning the point B will be tending to move down because the resultant direction is down, like pointing towards the tunnel. That means we have some kind of a shear loading in this intact rock bridge, and that will continue as we move on with the pressure transient. And this is an example of one particular pressure transient, and this will occur every time we induce a pressure transient. For example, let's say 1,000 times in a year, as we've seen from our previous results. And that can induce what we call a cyclic fatigue in the rock mass, which can affect or result in a failure at a much smaller load as compared to its strength of the rock mass.
I'm sorry to interrupt you now, Bibek, but
yes.
You're a little over time here, and there's only 2 minutes left, and there's a couple of questions here as well. So if you can please.
Yes, I will finish it now. Yes.
Yeah.
So quickly going on to the contributing factors. Of course, the orientation of joints and the type of block that we can create with these joints will be of significance. Here, these blocks will probably be already identified during the construction phase already and will be stabilized. But there will be some probably some type of blocks, for example, type 4 and 5, that will not be probably stabilized because this is not probably a potential threat of block fall during the construction phase itself. But as we've seen from the previous slide, fatigue can create such a situation where this will create an additional joint in the rock and create a situation where there will be a potential block fall. So that's one of the contributing factors. Again, joint void geometry. Tight joints will not conduct water and not create hydraulic impact, as for example in the upper photo here. Open joints or partly open joints like these, based on the roughness and aperture, will create a situation where the water will travel into the rock mass and create some hydraulic impact. Again, the deformational response of the rock mass, how stiff is the rock, will create or will affect the block fall, of course. Stiff rock will have smaller deformation, of course, as compared to weaker rocks. Here we see that the deformation is much higher when the stiffness of the rock material is much higher. The deformation is quite high, and that is also very natural. We've seen that the hydraulic impact also travels deeper into the rock mass when the rock mass is weaker. As you can see here, for the stiff rock mass, the hydraulic impact has traveled, at least the peak is here around 6 meters. But when the rock mass is less stiff or weaker rock mass, the hydraulic impact has traveled much more deeper into the rock mass. So the type of rock mass will also affect the results. And of course, the power plant operation, as I've already explained, will affect the results. Power plants without any restrictions against hydro peaking will have many stops and many load changes every year. And this will probably go on to increase as we have more wind and sun into the system. As I've already explained, shorter durations will cause large hydraulic stresses. And of course, tunnel dewaterings will also cause large hydraulic stresses and may initiate or trigger some fatigue in the rock mass, as we've seen during dewaterings. These are the factors, and until this point, I have explained how the fatigue mechanism develops, how the power plants are being operated, and how that affects the rock mass during each and every transient event. I think this is the summary of my results, which I've done until now, and I'd like to talk a little bit about the applications of the results that I've just explained. For example, the most readily applicable result is that we could probably slow down the shutdown or opening of a power plant without doing a lot of changes in the powerhouse, because it's just a behavioral change. We just have to be more aware that we need to slow down the shutdown so that we induce smaller stresses in the rock mass, because it's probably thought that this is not going to affect it that much, but when we do the shutdown slowly without doing any major changes in the power plant, for example, it's just as I said, a matter of changing the behavior of how we operate our power plants. I think that's a very readily usable application. And for example, if we go on to let's say go on to assess a potential blockfall situation in a dewatered tunnel or a new tunnel, the results can be used to assess at least a qualitative assessment of the rock mass situation. For example, what kind of a rock mass is there? Is it hard rock? Is it relatively weaker rock mass, for example? Is there open joints? Is there not like conductive joints? So the point is, if we have weaker joints with partly or open conductive joints, then we have to be a bit more careful with the support recommendations. We may have to be a bit more conservative in stabilizing our blocks or future blocks, because we might create some new joints by damaging the intact rock bridge, as I've already explained. And the third application is probably, for example, if we have some tunnels which have experienced very serious block falls over the years, we can use a similar method of instrumentation to actually figure out what could be the most suitable shutdown duration so that we could delay the fatigue of the rock mass. I think these are the three applications that I see can be used as a result of this research. These are some references I've used in the slides, and these are the publications that we've done over this research, and you can read my results and my work in detail in these papers. And these are all open access. You can just easily download them and read them. With this, I end my presentation, of course, and I thank you very much for your patience, and I'm open to questions. Thank you.
Thank you so much, Bibek. There's a few questions here in the chat, so I'll just read them to you and then you can answer them.
Sure.
And the first one is from Thomas Schönborn, and he asks, do you have examples of failures due to overloading of the rock mass because of shutdown?
Well, it's not failure of rock mass as we see here. It's probably not a result of one particular shutdown, but a cumulative effect of many shutdowns as a result of fatigue. So we cannot particularly pinpoint a case where we've seen a failure because of one particular shutdown. But as I said, this is a cumulative effect of a number of shutdowns. Yeah, so I don't know if that answered the question or not, but
yeah, I think we move on here. The next one are two questions from Hui Lu.
Yeah.
First one is, have you compared this effect with the classic rapid drawdown for the soil slope or embankment dams? And the question two, how do you simulate volumetric water content in the volume?
No, we have not compared that with classic soil mechanics examples, but I guess the mechanism is the same, like additional pore pressure behind the rock or the soil, but we have not made any comparison like that now.
Okay. And the second question here, how do you simulate the volumetric water content in the volume? Continuum model or joint DEM model?
This is a DEM model, yes. We have assumed in this particular model that the pore pressure in the rock mass, the intact rock pieces, are negligible because most of the pore pressure will be contributed by the joints itself. So this is a DEM model, yes.
Thank you. And I see also Henki Ødegaard came with a follow-up here on the first question.
Yeah.
Where it says that failure occurred on the USA hydropower plant air cushion due to the turbine rejection.
Sorry, come again, please.
He said that failure occurred on the USA hydropower plant on the air cushion due to turbine rejection.
Okay, thank you. I think that's the answer of the first question.
Yeah, it was.
Yes,
yeah.
Yes. Thank you, Henki.
The final question is there from Bjarne Børresen, and he asks, in a market that values flexibility, it may be desirable to increase the ramping rates, for instance, change load quicker rather than slowing down. Are there measures that can be taken when planning of constructing the tunnels to make them more robust and less susceptible to rock mass fatigue?
Yes, that's a very important question and a very important comment, for example, because as you mentioned, we might want our plants to be more flexible so that we can change the loads rapidly. That is the whole point, of course. But the summary is here that if we want to do that, we have to be a bit more conservative in the rock support. We probably need to install more bolts so that we can secure future rock blocks as well. And we probably may also need to, for example, seal very prominent joints. That could be one issue. And another issue is probably we can also increase the diameter of our surge tank so that we can increase the shutdown duration. I think the shutdown duration could be a bit larger when we increase the cross section of the surge tank, because then the rise of the water column during a pressure transient could be relatively smaller if we have a larger surge tank.
Okay. Thank you so much, Bibek. I think that was all the questions for now, and I see we're also a little bit over time. But thank you so much for presenting today, and thank you for everyone else for listening in. And then the next presentation in this webinar series will be in the beginning of November, and we will send out invitations for that shortly. So thank you so much, everybody, and have a great day and a great weekend when that time comes.
Thank you.
Thank you, and bye-bye.
Bye-bye.